Okay, we're going to continue now with talking a little bit more about some of these dynamics of rule-based systems, and particularly as they pertain to this idea of feedback. And there's different kinds of feedback, some kinds of feedbacks that allow systems to stabilize, and some kinds of feedbacks that push systems to change. So in order to talk about this, I want to introduce to you this idea of cybernetics. Cybernetics comes from a Greek word, and I won't be pronouncing this correctly, but the Greek is kubernan, which means to steer or guide. And from there, we get the word Kubernetes, which means a steersman, or the person who's got the oar and is steering the boat. Kubernetes goes to gubernator, which is in the Latin, and gubernator goes to governor, which is the English. So we can think of these words. Governor is really the word cybernetics, and you can think of systems that in some way govern themselves, and this relates back to cybernetics. I don't have an audience, but looking at my window, there's deer that are crossing the road outside the window. Kind of sweet. Two little baby fawns and their mothers, super cute. Okay, cybernetics. So cybernetics was a movement in the 1940s of a group of scientists and biologists who were very interested in thinking about self-governing systems because they wanted to understand how these systems could help explain some of the dynamics that they were seeing in different systems, but particularly systems that involved life. There was a group of these thinkers. They got together on an annual basis. There was something called the Massey Conferences in Cybernetics, and this body of thought became very influential. Cybernetics is really the precursor to complex adaptive systems thinking, but it looked at a slightly more limited class of complex systems. So let's talk about what that means in terms of self-governance. So if we think of this example of the Greek, the oarsman, let's think about the oarsman and what an oarsman is doing. The oarsman has got a target. They're trying to get to an island over there, and they've got an oar that helps them steer the boat. But there's also a number of inputs that they are receiving. So there could be currents, there could be wind blowing, there could be more weight on one side of the boat than the other. So if you had a static body of rules that said only just hold your oar at this angle and keep going till you get to the island, that wouldn't account for these different external inputs that you have to be responding to. In this system, what you have is your goal is to keep the eye on the target, and that becomes your input. If you see that the target is moving away from you, then you adjust your oar, you adjust your output until you see the target again. And you keep repeating this where you make an adjustment, you see if you're getting closer to the target, and if you're not, you make a new adjustment. If you are, you stay the course, repeat, repeat. This forms a system, and the system you cannot say is simply the oarsman and the boat. The system has to involve the target, that external input that is telling you what to do as the oarsman in order to keep the system stable, in order to keep it going towards where it wants to go. So cybernetic principles involve looking at a whole array of these kinds of systems that involve natural processes which permit life to be maintained in the face of changing environments. So how is it that we maintain our body temperatures at a steady state, regardless of how hot or cold it is outdoors? Obviously, you can get to extremes where we're not able to do that, but in general, we're able to self-correct how our body is operating in response to different kinds of environmental inputs. So there's this ability to self-correct within a context that involves a kind of a negative feedback. And when I use the word negative feedback, I don't mean negative in terms of how we would think about it, like a value judgment, that something is positive or negative. In the context of complex systems and cybernetics, a negative feedback is something that constrains the systems, that dampens change, that sort of keeps things more stable when you're having this conversation between an element and its environment. By contrast, positive feedback is something where you can have these amplifying dynamics where, for example, the rich get richer, or where you have videos that go viral because the more views they get, the more they are promoted, the more people see it, et cetera, et cetera. So that's kind of a cascading feedback that amplifies as opposed to dampening and constraining. This dampening and constraining is important in states where you want them to maintain a kind of operation, and we call that maintaining homeostasis. So another example of a complex system is known as the flyball or centrifugal governor. And this is invented by James Watt in 1788 as a system that is able to regulate itself, regulate the amount of steam that's coming into the system so you don't get too much steam, which would cause problems for the system. And the way in which this is governed is that if the steam input goes too high, there's a spinning governor, and that spinning governor will start to spin faster and faster, raising those fly balls. And as those fly balls raise, eventually they trigger a lever, and that lever raises a valve that cuts off the steam that then allows the system to kind of go back down to a more stable rate of movement. So I'm just going to have you watch a brief video of an explanation of this flyball system. Okay, here we go.
The important thing to realize about systems is how they are controlled. And we must get rid of any notion straight away that control is something imposed on the system from outside. It has to be built into it. Now, you saw me operate this governor just now and noticed how the engine slowed down. Let's see how the mechanism works. Suppose the engine is racing, then the governor flies open like that. You see it lifting here, transmitting the message along here, lifting that cam up here, and then shutting off a valve there. That is built into the system. It's called feedback, and feedback is ubiquitous in control systems.
Okay, the person who was introducing that system to you was Stafford Beer, and Stafford Beer is one of the key thinkers for cybernetics theory. So let's take a look at another system. This is a classic kind of cybernetic example, is the example of the thermostat. When you have a thermostat, it will have a target that it's trying to regulate the system towards. So this target might be that it wants to maintain 80 degrees. And then it's got a sensor, which is telling it an input. And so if an input is lower than the target temperature, then we turn the heat on. We then repeat. If the input then is too high, then we would turn the heat off, and we keep on repeating this. So we have this sort of system whereby the thermostat is maintaining its operations as part of a broader context where the thermostat doesn't know what to do and how to regulate the system until it gets the feedback, and then it keeps on adjusting. And this is the way in which the system is able to kind of control itself. We don't think about the thermostat operating separately from its context. It needs to have the context in order to provide the input in this kind of circular chain. If we look to another kind of cybernetic system, we can have very interesting systems where we actually don't have a known target, but where the system itself is kind of able to figure out a target for itself. So imagine that we have a rabbit population, and we're trying to determine what is the actual carrying capacity for a rabbit population within a given context. Every context will have its own carrying capacity, and we don't know what reproductive rate is at the best equilibrium within a particular context. So we have an unknown target, but we can still have an initial output, which is we let however many rabbits there are breed, and then there's a new bunch of rabbits. And if there's way too many rabbits for the food, then a bunch of rabbits are going to die and not reproduce. And if there's too few rabbits for the food, then those rabbits are going to be happy and eating and making lots of rabbit babies. So we can imagine that if there's too little food, then the overpopulation of rabbits will die. There'll be fewer to reproduce, and the system will start to get a little bit closer to that carrying capacity. The more we iterate through this with populations of rabbits, each iteration is going to get us closer to the point when the system will stabilize, and this is the carrying capacity. And so when we sort of think about systems that are operating harmoniously within their environment and how they magically know how many rabbits can live here, it's because the system itself has got an internal feedback mechanism that allows for the right levels to be achieved. This is a kind of a recursive causal chain, a system where as an element's state changes, it's affecting its own environment. And this altered environment is serving as an input that in turn affects the system's state. So you can't talk about the sustainable rabbit population without talking about the rabbit's reproduction, or the number of rabbits and the environment together acting in tandem with one another. In a way, this becomes a very, very, and I'll just go back for a second, it becomes a very, very holistic way of thinking about how a system can exert its own kind of self-control within a given context. Okay, I'm going to move on from that. So I want to turn to architecture and how some of these ideas were taken up by architects. So probably the most classic example is the Fun Palace, and you will have some readings about this, and there's also a podcast that deals a little bit with the Fun Palace. This was a paper project, a design that was never built, by Cedric Price, who was working with Joan Littlewood, who was an advocate for cybernetic thinking. And they worked together with a couple of cyberneticians of the time, Gordon Pask, who wrote a piece called The Architectural Relevance of Cybernetics, and Stafford Beer, who we saw on the last short video clip. Stafford Beer was involved in a project called CyberSyn, which was a project based in Chile. And the idea was that the government wanted to form a system of governance that would be self-correcting. So if you had to decide where to put money in terms of infrastructure, that you would test putting a certain amount of money out, and then you would collect feedback through sensors, and then that would determine whether you should adjust or do more or do less of something, or engage in a different activity. So it's interesting because sometimes cybersyn is discussed as a kind of a very sort of dystopian idea that algorithms are going to be controlling our lives, the system is a big computation. But in effect, it was almost trying to be the opposite. It was trying to say, rather than having government bodies that are people who are trying to, in a top-down way, impose what the system should do, that instead the system would be self-correcting based upon feedback of what is happening within a given context. So as it's receiving feedback in terms of what people are doing or what's working and not working, that the system would self-correct not through top-down governance, but because of a responsiveness to what is unfolding. So this much more nomadic way of thinking about how you would regulate a particular environment. So the Fun Palace was an example of architecture that unfolded by being governed or conversing with the users. In this case, the users and what they are doing provides the context. And the program in the Fun Palace wasn't sort of a conventional program where you have architectural spaces with designated functions, but was much more like a computer program. And just to clarify, because I wonder about this terminology of program, when we use the word program for architecture, we're talking about the design brief of what the building is going to have inside of it, and in terms of how it's going to function. And so in this case, the Joan Littlewood, who was initiating the project, said, we're not going to have a fixed program. The building is going to partially discover what it should be doing, what its target should be, based on receiving input from its users of what they are doing. And here we have this algorithmic functions, which we talked about before, that start to calibrate according to what we see people doing or not doing. So here's some diagrams of the Fun Palace. As I said, it was not built, but we sort of see some very interesting sections, and then this plan drawing that starts to kind of give you indications of things that are in motion and can alter. So the way it was intended to work was that raw data on the interests and activity preferences of individual users was gathered by electronic sensors. So here, again, I was saying that the individual use of that building becomes the input. The data was then compiled on, at the time, a very large IBM computer to establish overall user trends, which would in turn set the parameters for modifications of spaces and activities. So the parameters being, if something is being really activated, then that means that maybe we should do more of it. If something isn't being activated, then we can do less of that. Then the building was designed with movable walls and walkways so that it could adapt its form and layout to change in use, to respond to changes in uses. The program would constantly refine itself through these feedback cycles. So this was a building that was before its time, although today, as computer powering is computer power has increased, and as we have more sensors, we can begin to think, well, maybe we could actually create designs and architecture that were operating in a much more responsive way. In fact, in terms of architectural built projects, the Pompidou Center is probably the most direct descendant of Cedric Price's Fun Palace. It didn't have the sensors, but it did have this idea of flexibility. It was flexibility that has to be monitored by individuals instead of an IBM computer. But the intention was that you would put all of the building mechanics on the exterior, and then have an interior floor plate that could be flexibly reallocated depending on what needed to happen inside the exhibition space. So making that as free as possible, but still a lot more sort of manual input in terms of the system unfolding rather than an actual self-governance where the building could learn and change its walls without anyone having an input into the system. Okay. So just a couple of things more on cybernetics. Cybernetics tend to deal with systems that involve negative feedback, which suppress deviation from a goal or dampening feedback that is kind of serving to dampen change, suppress change. Control is an integrated part of the system. It's not external to the system. So there isn't something outside that is saying, how can the system be controlled? The system itself has these circular causal chains that regulate it from the internal dynamics. Now, I have to point this out because it's a bit of a sore point for me in terms of how people sometimes perceive cybernetic thinking. Norbert Wiener was, again, one of these people who was part of this early cybernetics movement and part of the Massey conferences. He's called the father of cybernetics. And he wrote a very unfortunately titled publications called Cybernetics, and the subtitle was, Or Control and Communication in the Animal and the Machine. And the word there that is the unfortunate word is control, because it tended to make people think that cybernetics was about some kind of computation that was going to control things externally, when in fact a much better term would have been self-correction. And how can we design systems that are able to self-correct through negative feedback, through perceiving, oh, what am I doing wrong in terms of my target? Here's how I self-correct. It's much more about an internal self-correction than an external exerting control over what's around you in some way. Complex systems, which I said are kind of like the child of cybernetics, are a little bit different from cybernetic systems in that they involve both positive and negative feedback. And because of that, they can evolve. So if we think about the thermostat before, I said that, well, we'll set a target and it'll be 80 degrees. In a complex system, you can have the thermostat figuring out that, well, maybe it shouldn't be 80 degrees, maybe it should be a different temperature. How it's no longer one steady target, but the idea that your target can keep changing. You can have a multiplicity of targets. And so these are systems that also alter in the face of changing environments, but they don't have this rigid goal. They can self-adjust what their goal is. It's still about a feedback conversation between an element and its environment, but it's about shifting from a given state. So now I go, well, gee, I was heading that way towards that island governing my ship, but now I see that there's another island over there, and I'm going to switch gears and go to that island. So how do we have systems that are a little bit more dynamic, that don't stabilize, but they keep on achieving a new dynamic equilibrium with their environmental context? Oops. Sorry. All right. So that's the last slide. We're going to turn in the next section to a few more architectural examples of how we can take up these ideas. And thank you for your time and attention.